So when picking spots, we give you some tools to assist you in finding out what a zircon is and what's not a zircon, considering we pour all of the heavy separates onto our mount before imaging and polishing. We have to differentiate between the zircon and the non-zircon. So initially, we will give you a printed out reflected light microscope image. You'll see that we have all of the standards labeled. The reflected light is used just to give you a map for where the standard's at. For uranium lead, you'll only be using R33, FC, and SLM. All of your unknowns will be poured into a large rectangle in the middle. If it's a detrital, for igneous, they'll be hand-picked about 60 grains. This mount in particular is also going to be run for hafnium over on the new, which is just next door, and standards for those are all labeled down here. When picking spots for the element, we give you backscatter and CL images to assist you. We will give you print-offs that are stapled behind the reflected light image. If you requested for both of them, they'll both be here. If one or the other, those will be the images here. So backscatter and then a CL image in black and white, but we will give you a colored image with the rest of your data and other files generated here after your visit. So on the SEM images that we do give you, when you're trying to pick zircons out, it's good to use the digital copies. We give you the printed out copies just in case you want to make any notes, circle any specific grains, or just have a very quick reference when you are scooting spots on the live laser computer over here. However, on offline targeting, we do suggest you use the digital images. First, we'll go over the backscatter images. So the image you see on the computer monitor right now is what the raw backscatter image looks like. It gives you different gray scale values based on the average atomic Z of the entire mineral. So for zircon, it is more or less just reading us a response back of the zirconium and silica and oxygen within the crystal itself. Since the most abundant, heaviest element inside of zircon is zirconium, the backscatter response from it is this very light gray, flat, homogeneous, like light gray color in backscatter. And so we image all of these standards as well as the unknowns when doing a backscatter. This is because we want to reference the grayscale value from the standards itself to the unknowns. So whatever grayscale these standards come in as, that same color, that level of grayscale should be true to the zircons within your detrital pour. So looking at the monitor here, we'll just observe what the grayscale level of these SL crystals are, since we know they are zircon fragments as they are our standards. We will reference this grayscale and then we will go look into our large pour of our detrital sample. So I'm just going to zoom into this little chunk right here, just because it has a wide range of grayscale levels inside of it. So if we zoom in, pretty close. We take these at lower resolution. High-res backscatters can potentially give you zonation information, but for a majority of the detrital samples that we run at LaserCron, we'll use low-res backscatter just to give a yes or no on zircon or non-zircon. So looking within this area here, we see several different shades of gray. We see a very, very dark, almost extinct looking grain right here, a more mild, lighter gray, but still rather dark, and then we get into the light grays of the zircons, and then you have these really bright white pieces, which are most likely some barite, which is the most common mineral that we see inside of detrital pores that have a brighter response than zircon itself. So since there's many different mineral phases within this sample, it's very, very important to reference this backscatter when picking spots on Mosaic, on any offline targeting computers here. If you do shoot any of these darker, less gray minerals, they may not affect the analysis or the mass spectrometer that much for the most part, but if you would terribly ever shoot a piece of pyrite or God forbid, a piece of galena, that would really screw up things within the mass spectrometer itself, and so we really want to avoid those, and that's the power of the backscatter, is that we have a definitive yes or no on zircon or not. What we do print off for you, since this one has a lot of black in it to save on ink and then to save on printing quality, we invert this image to give you a black and white. So just to show you really quickly what this black and white image looks like compared to that dark one, here is the inverted version of that last image. If we zoom into that same area, everything basically holds true to what I said, but inverted. So now the darker colors are the colors of the zircon, and the brighter colors are the non-zircon. So again, looking within that same region we were before, we can see that the darkest are those really bright barite pieces we saw in the non-inverted image. The zircon itself has a very similar dark gray response, while all the other non-zircons, the lighter minerals in these separates, are these light gray, verging close to white in their coloration. If we look at the same sample in CL response, we can get even more information out of it and maybe start to tell what some of these lighter crystals are. So in a colored CL image, on the monitor right now of that exact same sample we were just looking at, it gives you a whole lot of more information. Zircon in CL typically generates a blue to greenish yellow coloring, and we can see that within this sample here. So I'm going to zoom into that same exact area we have just previously been looking at, just to see what the differences are. So I'm pretty sure this is that area. If not, it should be pretty representative of the entire mount. So on the color CL, we can see a couple of interesting things. First, discussing zircons itself, you can see all of these blue and marginally green crystals are the zircon itself. A very soft pale blue, they could get to very bright blue, such as the rim of this grain right here. They can also be rather dark, which is more or less indicative of higher uranium concentrations. There can be very bright grains to very dark grains, but for the most part, the easiest way to distinguish a fluorescing zircon from anything else is the presence of oscillatory zonation. For instance, this grain, even though it is rather dark, you can see there's these pretty typical oscillatory growth zones of an igneous zircon. However, homogeneous growth is very common, which we observe in this grain and this grain here. One thing you may notice in this image as well are these large orange streaks. These are very typical of an apatite grain when it is CL'd. So it will fluoresce the same color as zircon, more or less. It'll be blue or this hint of a yellow-green, but it will have this tail of an orange streak, which occurs because of the phosphorus concentration inside of the apatite crystal. What it does is when it's excited by an electron beam, it fluoresces longer than anything else. So that's why we have these streaks, and they will always streak off to the right because that is how our CL detector acquires images, from left to right. So you'll see that streak out there. Most minerals do not fluoresce inside of CL, which is indicative of all of these really dark crystals. That just indicates no response, most likely not a zircon. The only way a zircon can be pitch black like that is if it has a uranium concentration that is very abnormal and that uranium is distributed evenly throughout the crystal. The main element that causes this fluorescence in a zircon is dysprosium 3+. And there's always variations within zones and within an individual zircon or its populations in its distribution of its dysprosium. So this is the color CL'd that we will give you in a digital file on your Google Drive. The print-off version that we will give you is what I'm going to display next on the screen here. We just invert it, make it black and white, and again the same principle of just saving printer ink and making a more crisp image in black and white. So if we zoom into that similar area, we will be able to see very similar trends that we saw in the colored version. We can see the oscillatory zonation, or the pretty typical zoning of a zircon, which you can see here. This is also pretty typical zircon zonation. All of those apatite pieces that we had seen earlier now are actually a bit easier to see. There are these darker, very homogeneous looking grains, and you can also see the streaking of that phosphorus signal from the electron beam in the SEM on this image as well. This will be the picture that we print off and give you in your paper map copies. A good use of the CL when you are have the paper copy is to just put a little spot on it indicating that you have that grain there. It's also really useful if you are trying to target a rim core pair. In this sample, for instance, there are a couple grains that may be of interest for that. Getting really close, pixels start to show up here, but for instance this grain here, this would be a very interesting grain to shoot a core, because there's this little nugget in the middle there that is perfectly rounded, while there's a growth out around it which has a different geometry, and that is generally a good rule of thumb when trying to pick out a rim core pair. If the geometries of zones don't quite match or they look off. So this would be a very nice candidate to do a rim core pair on to get a initial crystallization age and whatever it's been inherited, the country rock or whatnot, and then whatever igneous growth or metamorphic growth happened afterwards that grew around it. Trying to get the final crystallization age of that zircon, it would be useful to shoot the rim instead of the core itself. If you're trying to do provenance work and you have a bunch of grains with a lot of cores in it and a lot of rims, it would be useful to do several rim core pairs just to see what those trends are. For the most part, that is how you distinguish zircon and non-zircon using the imaging we get you. Also on the mosaic, which we will talk about, it'll be easy to distinguish what a zircon is compared to other stuff, just because zircon typically polishes a lot better than an apatite or even a little quartz crystal, and definitely better than barite. Apatite and barite are much softer than a zircon crystal, so when we polish it on our polishing setup up in our mounting room, those crystals tend to be more scratched, more cracked than a zircon, as a zircon's very resistant to our polishing processes. So once we have all of our images ready, we can then start picking spots offline, which we will do right now on any of our 3 offline targeting computers.